Hello everyone. In this video, we are going to discuss section 4.2, integer representations and algorithms. So this is the summary of this section. So we are going to first explain the base B expansion or base B expression. And then we will also discuss some particular bases like base 2, which is binary, base 8 is octal, base 16 hexadecimal. So these are the bases. They are very common in computer science and computer engineering topics. And next, we are going to discuss quite a lot of relevant algorithms. For those algorithms, we will show, actually there are some pseudocodes in the lecture slides, but I will show you these Python codes. And then we are going to also discuss the complexity of those algorithms. Some of them are very important because this efficient algorithm is required to implement some particular systems like cryptographic systems. All right, so let's go to the board. So basically here, when we are talking about this representation of a base B integer, so the representation is ak, let's start from ak minus 1, k minus 2, ak minus 3, to a0. And then we put the b here, indicate that this is a base. And in some textbooks, this is also called a radix. So because of that, there is a very important sorting algorithm called radix sort. Anyway, here we have a total of k digits. So these rules are as the following. So for every I, if I is greater than or equal to 0, less than or equal to k minus 1, then this AI coefficient AI should be greater than or equal to 0 and less than b. And then, so you can find that this is a universally quantified implication. It basically means that all the coefficients or all the digits, they must be in a certain range that is greater than or equal to 0, less than b. So you can also use another expression. So for all I is, if I is greater than or equal to 0, less than or equal to k minus 1, then AI is in ZB. So this is defined in the last section. So ZB consists of a lot of natural numbers, and n is less than b. Right, so this is the set builder notation of this. All right, so just now we have shown these requirements, and usually when we are using this k digit number, usually we also want to add another constraint, that is the highest ordered number is greater than 0. Right? But it depends. Right? Sometimes we require that, but sometimes we don't require that. Okay. Now let's continue to discuss these possible bases. So actually, the most common base that we are using is base of 10. Right? So when the base is 10, we call the system a decimal system. And for example, when we write is 1, 2, 3, and base 10. So by default, we are going to assume that this base is 10. So we simply write this 1, 2, 3 in a sequence. So this 1, 2, 3 is the representation of one number. And then, so we have many other base systems. I have just mentioned in the summary that these 2 raised to a certain power, particularly base 2, base 8, base 16, they are very, very common in a lot of computer science and computer engineering topics. So these are the essential bases. And besides this 10, 2, 8, and 16, so we also have some other bases. For example, when we are describing the time, we use base 60 for representing the seconds in a minute or the minutes in an hour. And then also in the to express the time, we could use this base 12 to express the hour, and this base 12 is also used to describe the month. In that case, we have the first month is January, the last month is December, the number 12, right? And for the hour, we also use base 24, right? So it depends, right? So sometimes we are using base 12, in particular in some clocks or some watch. So you can find in the this from 0 to 11, there are 12 hours. Right? By comparison, when you want to represent the hour in a certain epoch in the date, so maybe 24 is a better base. Right? And in addition to that, so we are using base 7 to describe different days in a week. Right? So we have from Monday to Sunday. And of course, in that case, usually we don't use the number, but still, there are a total of 7. You can consider that there are a total of 7 different digits. And finally, in the textbook, I think somewhere in the textbook, we have this ancient Mayan. They use base 20. Right, so base 20, I guess, because perhaps the most important reason that we are most familiar with base 10 is that we have 10 fingers. Right? So it's rather straightforward to count using 10 fingers. So for those ancient Mayans, maybe they are using 10 fingers and then they are using 10 toes. I mean, that will give them a total of 20 possible digits. Anyway, so now next issue. So for each number system, each base system, right? So we need to use different digits to describe the number in that system. Right? For the decimal digits, we are very familiar with. Right? So there are a total of 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, a total of 10 digits. And for binary systems, so we have binary digit or bit, and then there are 2 possible bits. And notice that this bit, bit, it is coming from the 2 words. So we take B from the binary and then this IT from the digit. So combining these 2, we get the bit. And as to the hexadecimal digits, so we have from 0 to 15. 15 is 1 less than 16. But usually in the to represent this hexadecimal number, we are going to use from 0 to 9, a total of 10. And in addition to that, we are using 6 English letters, A, B, C, D, E, F. Right? So A represent 10, B represent 11, and 12, C is 12, D is 13, E is 14, and F is 15. So at this point, I can just find that this is just a type of encoding, right? So we know this decimal number is, for example, 12, but we want to use a symbol. So in this case, this process is called encoding. So we are going to use a letter C to represent 12 in the hexadecimal system. Okay, so at this point, so we have basically explained how to represent a number in a base B system. Essentially, you can just list from the highest ordered digit to the lowest ordered digit. In particular, ak minus 1 to a0, a total of k digits. So we can use this sequence of digits, putting them inside a pair of parentheses, and then use the base or radix as the subscription. Right? So in that way, you can better understand these some other terms. For example, 1011 base 2, or 1011 base 8, 1011 base 16. So even though they are the same pattern, but depending on the bases, right? So they are different bases, so they are different numbers. All right, so in the lecture slides, the next issue is how to calculate this, how to understand this value, right? So there is a theorem for that. So let me again write this expression in order to represent this n. Let's say we have ak minus 1, ak k minus 2 to a1 and a0, a total of k digits, base b. So the value of this n, right, from this base b expression, we can find the value of n equals to summation I from 0 to k minus 1 a I times base raised to power of I. So this is the expression that we could use. Let me put this n here. N equals to this. So this is the expression we could use to calculate the value. So once again, we are most familiar with this decimal system. So usually when we want to do the actual calculation, we would like to use this summation of product to express the value of a particular number. All right, so based on this, so because of this this representation and the value, because of this relationship, so we have the first two algorithms. They are very easy to understand. So the first algorithm is base B expression to decimal, right? So I'm using this base B to 10 as the name of the algorithm, and then you can find here I have the first algorithm, base B expression to decimal. So the idea is very simple, right? Initially, I have an assert, so that is just to make sure that the base should be greater than 0. Maybe I forget to mention here. So this base B, it is greater than 0. And then I'm taking this k from the list, because I assume that the input A is a list of digits. So it's a list. Right, so k is the length of this list, or an array. And initially, I use this power, this p equals to 1, and initialize this s equals to 0. So this is corresponding to the to this summation, right? because in order to calculate this summation of the product of these two numbers, we will need b square b to the power 3 and eventually b to the power of k minus 1. Right? So to calculate that, so I'm using a parameter p to get this sequence of powers. And then since this is a summation, so you can find that outside the for loop, I initialize an s to 0, and inside the for loop, in each iteration, I'm adding s equals to s plus ai, that is the coefficient times p. Remember that initially this p equals to 1, so when I equals to 0, so this p is actually 1. So a0 should be multiplied by 1. And then at the end of this iteration, I have this line, p equals to p times b, which means that I'm going to calculate from b to, from 1 times b equals to b, and then the next iteration, b times b will be b squared, and then the third iteration, at the end of the third iteration, I have this b to the power 3 equals to b times b squared, and so forth. Eventually, we have this b to the power k minus 1 will be used in the last iteration. Anyway, so it's a very simple algorithm. And you can also quickly identify that here in this algorithm, if we skip all these lines about the asserts, just consider the comparison as the operations. So this algorithm actually has complexity big O of k. Right, so that is clearly listed here. Suppose k is the number of digits. K is number of digits in the base b expression. Anyway, so that is the first algorithm. Based on this summation, this value of this number and then the representation, we can also derive this base b expression for any given integer. At this point, let's assume that this integer it is represented by decimal system. So the algorithm is shown on page 26. So for this algorithm, it is called base b expansion. So we have the number n and a base b. Apparently, we want this b to be greater than 1 in this case. And then we have this. So initially, we let this q equals to n and k equals to 0, and then using a while loop. Each time, we are going to do the integer division to find the quotient and the remainder. So the remainder will be the coefficient, and the quotient will be used in the next iteration. So then we have this k equals to k plus 1. So this is the pseudocode. So in Python, so this is the actual Python code. I can actually change this to make sure that this base is greater than 1. Anyway, as I just explained in this in the slide for the pseudocode, so we are going to have some iterations, and in each iteration, we calculate one coefficient, and then we are going to calculate the coefficient from the least significant digit to the most significant digit. in this sequence. So that is why here I have 3 lines outside the while loop, because I want to make sure that even if this number n is 0, so this whole program is still running correctly. But of course, there could be other implementations. I'm just trying to simply trying to make it correct in this in my assumption that the output should be a list of coefficients. All right. So the first remainder will be the least significant digit. All the rest of the digits will be appended, appended to the list. And then after we find the least significant digit, so this n equals to n divided by b. So this is an integer division, right? An integer division in Python. Next, so this, as I have already explained for the pseudocode, right? It basically, we are going to use a loop just to find all the possible digits, and eventually return a list of digits in it's a list or just an array. Let me execute that. Now here we have first test. Suppose I have a number 123. I already explained that previously, right? So this 123, when we don't write any base, so we assume that the base is 10. So in the program, I first try this base 10. I'm going to show you in other bases in a few moments. Right? Then I'm calling this base b expression. So n is an integer here, and b is the base. Remember the first in the first experiments, we let b equals to 10. So the program next print the base b expansion of an integer of decimal number n is a list. So at this point, I'm using this this method to print this the coefficients in the list in the reverse order. Right, so this is because in the list we store this A0, A1, A2 in this order, but in reality we are more familiar with this from left to right, from the highest order to the least significant order, least significant digit. Right? So eventually I call this base b to 10 because I have introduced these two algorithms, and try to see whether or not after we converting this sequence of digits back to the original number, we still have the same number in order to verify the correctness. Right? Apparently it is correct. So 123 in base b system. So the list of digits, if you write this from the highest order or the most significant digit to the least significant digit, then we are going to have 1, 2, 3, these 3 digits in the list. And then when we convert that back, we get exactly the same number. Right? So now let me change this number to 2 to see what is the binary form. You're going to find that the base 2 expansion of 123 is 1111011. So we have a total of 7 bits. Remember, in binary system, we call binary digit bit, just to simplify the term. If I change this to 8, so this 123 in an octal system, which is a base A system, it is 173. 173. Remember that we have to call that 173 instead of calling it 173 because the base is 8 in this case. And if we change this to 16, then we are going to get 7 and 11. And remember that in the hexadecimal system, we have this mapping, right? So when you see this 11, you should map that, you should encode that using letter B. So 7B represent hexadecimal number 7B represents decimal number 123. All right, so after doing all these experiments, we can verify the correctness. And about the complexity, I already explained the first algorithm, that is to calculate the value of a base B expression, right? To calculate that value, so the complexity is big O k. Well, k is the number of digits. Right? K is the number of digits. And then, so in order to convert this, to generate this base B expression, so we are going to use this base B expansion or base B expression. So the complexity is big O. Let me write this here. Maybe this is more clear. Base B n. So you can actually also skip this base of B. Just use this log of n, right? Because log base B n equals to log base 2n divided by log base 2b. And log base 2b is a constant, so we can use this. Right? So in this way, it looks simpler because now we don't have this base. But since this is correct, because when we are using this big O notation or big theta notation, so it doesn't matter what exactly is the constant coefficient of this expression. Right? So this base B, base 2, when you are using the big O notation or big theta notation, so you can use any integer that is greater than 1. So it doesn't matter. Okay, so in the lecture slides, you can also find some other examples. For example, on page 22, we have the binary expansion. Binary expansion is 1, 0, 1, 0, 1, 1, 1, 1, 1. So this in the base 2 system, so I have this program here, 1, 0, 1, 0, 1, 1, 1, 1, 1. Right? So for this base 2 expression is binary number. So I want to first print this expression. So actually, I first do this reverse the order, right? Because as I say, so this is the order we are very familiar with. But in order to save that in the computing system, actually we are saving this lowest, the least significant bit first, right? And then we have this base B, base 8 expansion, and then I try to convert that to a number, and then converting that back to binary. Right? So eventually, you're gonna find that this. Where is this base? It's 2 expression. One zero one zero one 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 one, and the corresponding decimal number is 351. And so that is here. And also, when we convert that back, we are going to get this. But keep in mind that this is just for illustration only, right? In that system, the actual list, we are saving all these sequence in a reverse order. And then let me execute the next line. Suppose we have a binary number 11011, 11011, using this conversion. So base B to decimal, base B to 10. So I try to convert this to decimal number. Execute this. So 11011. So this decimal number is 27. 11011. On page 23, we have this base 8 system, which is the octal system. Here we have 7016 in base 8. Right? You're going to find that if you want to do this calculation, 7016, converting that to decimal, you should get 3598. 3598 in the decimal system. And then this 111 in the octal system, again using this algorithm, so you should be able to find this number is 73. And the next page shows the hexadecimal expansion. So we have 2AE0B in the hexadecimal system. But as I mentioned, these AEB or other English letters, so they are just some encoding of a number. So because of that, I'm going to change this A to 10, E to 14, and B to 11. Right? So in the hexadecimal system, so we have these 175,627 for 2AE0B. 175,627. The next example, which is a little simpler, is to expand hexadecimal expression 1E5. So 1E5 in the list, I'm using 1, 14, and 5. Reverse the order, and then for now we are going to use this from lowest, the least significant digit, which is 5. The next one is 14, is the letter E, and then the most significant digit is 1. Right? Reversing the order, then convert that to the decimal and converting it back to the this. And there's some minor mistakes. All right, so it's 485. And on page 27, here we have another example just to find this octal expression of number 12,345. Right? 1, 2, 3, 4, 5. Base A system. So we are going to have 30071. 30071. And in the next few pages, you're going to find that if you already have a binary or octal or hexadecimal, you have a simpler way to find. In particular, so it shows that from this binary, actually we can partition these the bits in a sequence of blocks. And then using these blocks, so we can quickly convert binary to octal or convert binary to hexadecimal. So that should be very easy to understand. And on the other hand, if you have hexadecimal, you can change each digit in hexadecimal to 4 bits. Right? From octal to binary, so we can use 3 bits to represent every digit in octal. So to briefly summarize, so here we have the conversion. So that is, you can consider the binary is in the middle. So there are actually 2 very simple rules to convert binary to octal or convert binary to hexadecimal. using this binary as the core, if you want to convert octal to hexadecimal, you can convert octal to binary first and then to hexadecimal. And on the opposite direction, also you can do the same thing, right? Convert hexadecimal to binary, just replace every digit in hexadecimal by 4-bit pattern, right? So you are going to get a binary number, and then using 3 bits in a block and convert each block to a digit in octal system. All right, so next we have a few algorithms. The first one is called binary add. Right, this binary add is very simple. So actually at this point, so we are trying to explain this binary addition using software. So in practice, so in most of the cases when we are doing the addition, we are not using software to do the addition. Right? So you have to be very clear. So in practice, most of the time when we are doing the addition, we use the hardware. In particular, we are using the logic circuit to implement the binary addition. But the idea of this addition using software is pretty clear as well. So suppose we have a sequence of bits. So once again, let's start from the most significant bit to the least significant bit. So that is A with subscription n-1, n-2 to A0, representing number A, and B subscription n-2, B sub n-1, B sub n-2 to B0 to represent B. Remember that these two representations, they are binary representations of the two numbers. So what we are going to do is that we initialize a C, which is the carry. Carry is initialized to 0. Then in the first round, we are going to add A0 by B0. Right? A0 by B0. So what happened is that A0 plus B0 plus C, apparently the first time we execute this line, so C is 0. Right? So and then we try to divide that by 2. Actually, you can think about this is actually the integer division. So we are going to get let's say this D divided by 2, this is the new carry actually, right? And then on the other side, we can get the sum. So this is by using this AJ plus BJ plus C minus 2 times D. But anyway, so the idea is pretty clear. So I also have my own my own Python program. So the first few lines are used to because as I explained previously in my example, I'm using a list to represent this number. That is using a list of digits to represent any number. So it is possible that these two numbers, they may not have the same number of digits. So these are the lines that I'm trying to do a pre-process, right? Pre-processing the input AB such that I'm going to have this a total of n digits for both of the two numbers. And then you can find that initialize C carry equals to 0, sum. Keep in mind that I'm using the a list to store the representation. So I initialize an empty list. Then for j in range n, so T is the sum of the AJ plus BJ plus carry. And once we have the sum, the integer division T divided by 2 will be the new carry. And the sum for that particular digit is the mod operation, T mod 2. Right? And eventually I append this S to the list. And after we finish this iteration, the for loop for J, so maybe there is a final carry. So if necessary, I'm going to also append the final carry to the list and return this list. And next we have a simple example. So you're going to find that, let me put this here. No, this. So in this example, I'm trying to add 17 by 4, right? So 17 is represented by binary 10001. So you can actually very easily verify because the first one is corresponding to 2 to the power of 16. So we have 2 to the power of 4, that is 16. 16 plus 1 is 17, and 4 is 100, the binary. So after I call this binary addition AB, what happened is that first, these two lists, they will have exactly the same number of digits. I already explained. So this is due to the fact that I'm trying to make sure that these two binary numbers, they have the same number of bits. Right? So after I execute this binary addition, so A in this case is the same, but B, I append two zeros in the most significant bits. And the sum, the addition is 10101. Right? This 10101, if we use this base bit to decimal, converting that back to decimal, so 17 plus 4 equals to 21. So this equation is the equation we should be very familiar with. Right? And in the next example, I'm trying to add 17 by 0. So once again, if I put these two print lines before I call S, so we should find that A is 10001 and B is 0. But after I call that, so I have some zeros in most significant bits. But anyway, so the result is still correct. 17 plus 0 equals to 17. So anyway, so for this algorithm, so we have this complexity big O k, where k is the number of digits in the large number in the addition. Right? All right, so I think that should be very easy to understand. You could use this big O n. It just depends on the definition. So I'm using this number k is because I used k previously for algorithm 1 to represent the number of digits. So I'm going to continue using this k as the number of digits in the large number in the addition. All right, the next example, the next algorithm in this section is the multiplication, right? Binary multiplication, multiply. So you can find this algorithm, the pseudocode of the algorithm, on page 31. So for this, so I'm going to find that actually, so I'm going to initialize P, right? This P as the product of the product after we multiply two numbers A and B. Right? Initialize that as a list. So when B0 is 0, the idea is that we are going to create a list with just one element that is also 0. So the idea is that, so in the initialization stage, if B0 is 0, then B0 times anything, it is still 0. So the binary form, when we multiply this A with B0, let's say we have A times B0 equals to 0 if B0 equals to 0. If B0 equals to 1, so it is A. So it's a very simple equation, right? So this is the initialization stage. And then for J in range from 1 to the LB, this LB stands for the length of B. So I'm going to shift all the bits, to the left for 1 bit. So I'm using a for loop to do the shift. But in reality, when we actually are using these bits to represent a number, so all this can be done in hardware, right? So this is just used to illustrate. So later on, when we analyze the complexity, we are going to simply ignore this part. Anyway, so this is just shifting. Right? And then after that, we're going to check whether or not Bj equals to 1. If Bj equals to 1, so the new product will be the result of a binary addition P and A. Remember, at this point, the A is a shifted version of A. So eventually, I let this P equals the new product P, new P. Right? So the idea is that when we have BI, right? Because when you have BI, so the corresponding number is BI times 2 to the power of I. Right? So A times BI times 2 to the power of I equals to A times 2 to the power of I times BI. It equals to, so it equals to 0 if BI equals 0. It equals to A times 2 to the power I if BI equals to 1. Right? So this is very similar to the equation we have. Right? So the idea is that when we have this BI times 2 to the power of I, multiply it by A, so we are going to have this component, this scenario. So suppose we have a temporary product. So that temporary product P should be added by this number. So that is why in the program, so I have this if statement, if Bj equals to 1. So that is because when Bj equals to 0, so this product is 0. So P plus 0 equals to P, so nothing is changed. But if Bi equals to 1, so this product equals to Ai times 2 to the power of I. And remember that after each iteration, I first want to shift all the bits to the left for 1 bit. So the corresponding number will be Ai times 2 to the power of I. Anyway, after this class, maybe you can write your own code, right, based on my program, and test that by yourself. So next, I'm going to just simply test that. Right? If I change, let A equals to 17, let B equals to 4. So first, I'm going to create a list by calling this base B expansion. So A is the number, the decimal number A, and the base is 2. For B, we are doing the similar thing, and then call the binary multiply AB and get P. So eventually we have A is the list of bits 1, 0, 0, 0, 1. B is 1, 0, 0. We have shown this in previous examples, right? And following that, so P equals 1, 0, 0, 0, 1, 0, 0. The corresponding formula in decimal is that 17 times 4 equals to 68. So we can change this to other numbers like 17 times 5 is going to be 85 and so forth. And in terms of the complexity, so here I list that the complexity is big O k squared, where k is number of digits in the larger number. Sorry, this is, I need to revise that a little bit in the multiplication. Right, in this multiplication. So this is because when we check this code, you're going to find that there is a single for loop. Right? For loop all the bits for B. And I already mentioned that it's shifting operation. So even though we use use a for loop to do the shifting operation, but in reality, in practice, we can always do this by shifting some bits in the memory. So we don't need too many operations. What maybe may relate to the complexity is here, this line, because we need to call, in the worst case, you can imagine that in the worst case, so all the bj is 1. So you need to find the new product by calling binary addition. And remember that previously we analyzed that the binary addition is big O k. Right? So combining this, so this complexity of this line is big O k, and we will do this up to k times. So together, so the worst case complexity will be big O k squared. Right? So that is the complexity. It is also shown on page 31 in the lecture slide. So, but in this case, the author apparently was using letter n. But you have to understand that. So in the slide, this n actually is not that number; it's the number of bits. In my program, so since I'm using k to represent the number of digits, so the complexity is k squared. So finally, we have two very efficient algorithms. The first one is called binary exponentiation. So the idea is very simple. We want to find an efficient algorithm to calculate b raised to a certain power n. So to calculate a base raised to exponent n, so the trivial implementation is that you have b times b times b times b. So we have to do a total of n minus 1 multiplications. So this is certainly not efficient, right? Certainly not efficient. What is more efficient is that actually you should observe that this n could be represented by binary. Let me use an example. Suppose we want to, let's see what is the example here. 3 to the power of 11. 3 to the power of 11. Using the trivial implementation, we need 10 multiplications. So in this case, if multiplication is the operation we are going to count, so we are going to have n minus 1. Right? So this complexity is go n. But observe that when we represent this exponent n by using the binary form, 3 to the power of 1, 0, 1, 0, 1, 1 in binary. Right? So it could be represented by 3 to the power of 1, 0, 0, 0 binary times 3 to the power of 1, 0 binary times 3 to the power of 1. So the corresponding decimal digits will be 3 to the power of 8 times 3 to the power of 2 times 3 to the power of 1. So at this point, you're going to find that actually when we are using this n, so the number of digits, number of bits will be log n. Right? When n is the exponent or power, so the number of these bits will be log n. Right? So in order to calculate all these, for example, if we have 3, we can calculate 3 squared equals to 3 times 3. And then when we have 3 squared, we can calculate 3 to the power of 4 equals to 3 squared times 3 squared. And 3 to the power of 8 equals to 3 to the power of 4 times 3 to the power of 4. So in other words, for each single bit, right, in the exponent, we will need to have one multiplication for calculating this 3 to that power, and we also may need one more multiplication to calculate the 3 to the power of 8 with a temporary result. Right? So essentially, we can imagine that we can establish an inequality. Right? So the number of multiplications should be less than 2 times log of n. Less than 2 times log of n. So the complexity is big O log n. So the operation is multiplication. So this is a little different to what we have in previous analysis, right? Because for the binary exponentiation, it would be easier to use multiplication as the basic operation. Anyway, now let's see this execution. So by doing this, as I already have explained, so from the simple and trivial implementation that requires big O n, so now the binary exponentiation algorithm, the complexity is big O log of n, which is much, much smaller. And in the lecture slides, actually, you are going to find this binary modular exponentiation. Right? So it's very simple, very similar to this binary exponentiation. So the difference is that now we want to calculate b to the power of n modulus m. So since we already have this binary exponentiation function, right, so what we need to do in the next algorithm is just to use the mod m operation for each of these multiplication. Right? When we do the multiplication, we will find the remainder by dividing the product with m. So eventually here we have, for example, 3 to the power of 21 mod 11 is 3. And let's go to check this example. Right, so here 3 to the power of 11. Oops. Apparently here this is not exactly the modular exponentiation, because here the example doesn't show the modular. But anyway, so we are going to find this algorithm. So it's going to be log n, as I say in previous discussions. But in this case, apparently the author was using this log m square. So this is because we are using different units, right? when we are using this big O log n, so the operation is multiplication. So if you want to consider the multiplication complexity, you can take into consideration that if we want to do the binary multiplication, the complexity is big O k squared, where k is the number of digits. So that is why here in the lecture slides, you can find this log m squared. Right? So this is an expression slightly different to the expression I show you on the board, mainly because we are using different operations as the basic unit. Actually, this is a very practical issue. Later on, you're going to find that, even though we may not going to further discuss that, but you can find in the lecture slides. So there is a very important application of this modular exponentiation, that is for the public key cryptography. In a lot of public key cryptography, and in particular in this RSA algorithm, RSA encryption, RSA decryption, we will need to do this modular exponentiation for very large number. You can find a little bit some discussions on this page 98, 99, and 100. So you're going to find that in this RSA algorithm, people will need to generate a very large integer n that is a product of two prime numbers. Each prime number could be, so I think this 200 is not big enough. In today's standard, it should be more than 300 digits, decimal digits. That is more than 10,000 bits. 1024 is minimum. Sometimes people use 4,000 bits, 4096, 4,000 bits for each of the prime integer p and q. And then we find the product n, right? So it's going to double. Like you have from 2,000 to 8,000 bits. So that is a very large number. And when we have that large number, you're going to find that, so this E, which should be chosen from a certain range, but you can, roughly speaking, I mean, thinking about this, E should have also very large number of bits, like more than 1,000 bits. Right? So here, to encrypt the message, so given an input message m, which is represented by an integer, we want to calculate the modular exponentiation m raised to the power of e mod n. Remember, these e and n, they are very large numbers. E could be integer more than 1,000 bits, and n could be integer with more than 8,000 bits. So in that case, so this efficiency of modular exponentiation is critical, right, to this whole system. And in a similar way, on the next page, page 100, you're going to find that this decryption is using a similar expression. That is m, that is the message we want to send, equals to c, that is the message actually appears in the communication channel, c raised to the power of d mod p and q. So this is n, right? So again, these c, d, and n, they are all very large numbers, right? So as a result, so when we are implementing this RSA encryption and decryption algorithms, we have to make sure that we are using the efficient algorithm, that is the binary exponentiation algorithm. All right, so now let's stop here. So if you are interested about these more topics about number theories and applications in cryptography, you can take an advanced course called Network Security and Cryptography, which has a lot of discussions about different algorithms and also about the complexity of those algorithms. All right, so to briefly summarize, so in this video, so we have discussed the integer representation. So we explained that, so in the integer representation, the most common representation is a sequence of digits, right? And we also have to specify the base. And In practice, we have base 10, base 2, base 8, base 16. We should know the encoding, right? So in each system, so there are a limited number of digits. And then given the common representation, we use this summation of product form to calculate the value of that integer. And then we explain some algorithms. You can review previous parts of this video to see more details. And also for each algorithm, we discuss the complexity. And that's the end of this video.